go. Alright, so this is what STAT will give you back. It will give you back a structure like this. If you look down here, you can see that it's got a whole bunch of weird operating system types, some of which are kind of obvious. Time, maybe that's not so obvious. User ID. So every user on the system has a unique ID, and I've forgotten how to get access to it, so I won't bother trying. Groups similarly have a numeric ID. They've also got a symbolic name. So of course you can always ask something like that. What if I do that? No, it's not going to help. Look, I'm logged in a whole lot of times. And if you do ls-l, of course, you get, that's the user, that's the symbolic name for the user, that's the symbolic name for the group who happens to own this particular file. That's the size in bytes. That's the last time it was modified. So remember that there are 3 times associated with the file: when it was last read, when it was last written, and when it was last, when its status was last changed, like if you do it to mod. So this ls always just shows you the date it was last modified. And I'm sure if you want to go and read the manual page for ls, you'll find a way to get it to show you the other timestamp values as well. What else have we got? The block size. So remember that standard I/O deals with buff size buffers, and buff size is generally 8,192 characters. A typical file system may not have blocks that are that large, maybe they're a little bit smaller, but in any case, you can tell it what's the optimal size to read chunks of data from the device where this file is stored. And similarly, well, not kind of related, you can find out how many blocks of data this file comprises. So 512. And it's measured in terms of 512 byte blocks, so you can tell how old it is that this field was added, because nowadays blocks aren't 512 bytes, they're typically a bit larger than that. And there you got those 3 times. So all of this info is associated with each file in the file system, and you can access it using STAT. And the mode, well, you can see all of those mode values there. The useful ones are the permissions for the various types of users, and also what kind of file it is. We'll be talking about some of these other kinds of files later. If you want to make a directory, you can either use the make-dir command at the shell level, and I can say make-dir xyz. If I do ls-l, it'll show me there's a new directory with those permissions, owned by me, owned by that group, and it's called xyz, and it occupies 64 bytes, even though there are no files in it. Well, in fact, there are 2 entries. There's one for itself and one for its parent. So if I was to do that, I can see those 2 entries there. What else is interesting about that? Nothing much really. So you can make directories from inside your C programs, basically. Sync. The way Unix works, and the way most operating systems work, is that when you write to a file, you're not actually writing directly to disk. If you had to do that every time you did a write, things would end up being very slow. So most operating systems will have a whole bunch of buffers, and these are extra buffers, so we know that standard I/O, a file star, one of the components of that is a buffer. An 8K buffer. If you fill that buffer up and you write it out, where it actually goes, it goes into an operating system buffer, and eventually it makes its way to the disk. So there's a huge amount of buffering going on behind all of this stuff. So in any case, if you've written stuff to a file and it's really important that that stuff ends up on the disk, and typical application where this becomes important is in database systems and transaction logs. We want to make sure that the fact that the database has been changed is definitely recorded on the disk. And the way you can do that is use this fsync function. So that will push out any data that happens to be in an operating system buffer that's associated with this file of this group data. There's a kind of standard I/O analog of that, flush, but that doesn't copy data onto the disk. It simply transfers it from your standard I/O buffer into a file system buffer, and from there it will eventually be written out to disk. So if you really wanted to make sure, you could do flush followed by fsync to make sure the data is pushed out. Alright, so what do file systems give us? They give us a nice way of referring to objects that are sitting on the disk. Jushenk gave a nice example in his lecture about the fact that data is just chunks of bytes in a particular location on the disk, and ultimately you've got to refer to that location to read that chunk of data in. One way to refer to that location is just to say disk number 5, track number 14, sector number 46. That's not a useful way to refer to files, so it gives you a nice abstraction where you can talk about file names. Allows files to be arranged in a hierarchy of directories, and so on and so on. So that's one of the functionalities that an operating system provides. It provides all of these other kind of functionalities as well, and we'll talk about each of those in the next couple of weeks. And the first one to look at is memory management. So here once again is our typical computer system architecture. We've got the CPU, which is where all the action happens, where you add two numbers together and so on and so on. And in order to do that, you can get those numbers from the RAM by doing load word in MIPS, and if you want to push stuff out there, you can use store word to go from the CPU to the RAM. Most modern computer systems won't just have the registers in the CPU and the random access memory. They'll typically have a layer of faster memory in between the CPU and the RAM. So CPU is really fast, accessing the registers in the CPU is really fast, accessing RAM is slower, but still very fast compared to accessing from these kind of devices. Cache is faster than RAM, so you've got this hierarchy of speed. Very fast, pretty fast, slightly less fast, and extremely slow. Okay, so what we're interested in now is a process is running on the CPU, and it's going to be manipulating memory. And for the time being, I'll just forget about cache and just talk about RAM and the CPU. Alright, so I've said process a couple of times. So what exactly is a process? It's an instance of an executing program. So when you type /a.out or /slist1, you start a process running. While that process is running, it has a whole lot of information associated with it, like it's got a stack, it's got values of the various data objects, it's got its code. The code is actually, hopefully, static. You don't want the program to go changing during its execution. Maybe there are some situations where you do want to do that, but generally you don't. So we've got all of this information is ultimately stored in the random access memory. It may start life on the disk, but it has to make its way into RAM before you can actually start doing stuff with it. So we've got the code segment, we've got the data segment. Code segment typically read only, data you can read write. And then of course you've got the values in all of the registers. So while the program is running, you know, if you sit there and look at Qt Spin, you can see down the side of the screen there's a bunch of values for all the registers. If there's a tab in Qt Spin, you can go and look at what's in the memory. So all of that stuff taken together comprises the current execution state of the program. On a typical machine nowadays, and back in the good old days when we had ENIAC and a lot of valves, there was one program running at a time. So you just load that program in, that program would execute, it would finish, and then you'd load another program in and execute it and finish and so on. Nowadays, you've typically got dozens of processes running on the machine at any given time. Here's what's running on this laptop. Whoa, wasn't expecting all that rubbish, but there you go. And I could scroll a long way through that, and maybe it would have been better if I'd done PS, just AX. I think use, yeah, right, that's looking a bit better, blah, 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 blah. I'm not doing much, all I'm doing is running a browser and a terminal window, but there's all this other stuff running at the same time. So that's actually a hell of a lot of stuff running. So multiple processes are active in the sense that they're in a state where they can execute, where they haven't completed their computation. Some of them, well, exactly, because this machine's got two CPUs, exactly two processes could actually be executing at the same time. All of those other processes are just going to be sitting there waiting for an opportunity to execute. So those processes are suspended. So clearly, when a process is suspended, its runtime state isn't sitting in the registers in the CPU. What's happening in the CPU registers is whatever the currently active process is doing. So if a process gets suspended, we have to somehow store the entire current execution state of the process. So all the registers have to be saved somewhere. All of the data, all of the variables, the contents of the stack, all have to be saved somewhere, so that when the operating system lets that process run again, it can grab all of that data, stick the register values back in the registers, load up the RAM with the appropriate data from the stack and so on, and then it can start the program running again. So it's got its entire state restored and off it goes. One really nice abstraction that operating systems provide is that processes don't know about each other unless they specifically want to communicate. So basically what a process wants to think, I'm the only thing running on this machine, nothing else is going to interfere with me. I start running, I do all my execution, and eventually I stop. In between, the operating system might stop me, but as far as I'm concerned, that's completely invisible. I don't know that I've stopped, and the operating system will restart me, and I'll just keep going from where I left off. Might get stopped again, paused, restarted, and eventually I'll finish. But as far as me, the process, is concerned, I just start executing and I run all of my code until it finishes. And I don't see anything else in the operating system. So remember the memory model that a typical C program has. We've got the code loaded in the lower part of memory. We've got global variables. We've got the heap, where all the malloc stuff goes, and we've got the stack. Starts at the top of the memory and grows down. So that's what the program wants to deal with. That's, as far as it's concerned, that's the memory of the machine. And all of my stuff is loaded in memory, and I can just go away and do, you know, the kind of stuff that scroll.s is doing. Of course, I'm not really the only process on the machine. I might be process one, but there's, as we saw, hundreds of other processes running simultaneously. As I said, I don't know about unless I want to talk to them, and we'll talk about how processes communicate later on. Right, so back in the days of ENIAC, this was really easy. You just load the program into the machine's massive 200 byte memory and start it running. And the program runs and eventually computes the result and finishes. So one important thing to note, or a couple of important things to note, the process can use as much of the memory as it likes because it really is the only thing sitting on the machine. All the addresses within the program, if I reference address 1000, then address 1000 is going to be at address 1000 in the physical memory. So every address in the program corresponds exactly to an address in physical memory, and of course the stack pointer register is initialized to the top of the stack, wherever that happens to be for my process. I'm not sure why this process didn't use the entire memory, but it didn't. So I started the stack here. That's all of my memory, and as far as I'm concerned, that's the universe, and that's what I deal with. So that's fine if you only want to have one process running. What if you want to have two processes? Well, the first process can be just like I described. I could stick it starting at address 0 and make it, however much memory it needs to use. That's what I could do. But what if I want to put a second process into the memory at the same time? It obviously can't start at address 0 because the first process is there already. So a sensible way to do things, first process is at the lower end of memory, second process I can stick it there, however big it happens to be. Now that's potentially a problem because I said that all the address references inside the code refer to absolute addresses. So if in here I've got load word from address 1000, I know that address 1000 corresponds to the memory cell at address 1000, the physical memory cell at address 1000. If I've got load word address 1000 here, I don't want to talk about physical memory address 1000. What I want to talk about is address 1000 inside my address space. My address space starts at this address here, so address 1000 is actually at P1 size plus 1000. Okay. So that raises some challenges. Loading this process in is fine. You can just load it into memory. You don't have to fiddle around with anything. When you load this one in, potentially what you have to do, as you're loading it, you look at all the code that's going in, and every time you see an address, you add this value to it. And so all of the addresses will then become relative to this, and they will all make sense in the context of the memory space for this process. So that's one way you could do it. So that was what I just described there. Another way you could do it is to map the addresses during the execution of the program. So the program starts running, and somewhere you're going to have to store where is my base address. So for process 1, my base address is 0. For process 2, my base address is P1 size. And every time you make a memory reference from inside the code, you add the base address onto that. So that will generate the correct address at runtime. Now clearly that's going to slow things down a little bit because you're not directly loading, here's an address, load me stuff from that. Here's an address, calculate the real address and then load stuff. So it's clearly a bit of overhead going to happen there. Alright, that's okay for 2 processes, but it actually scales to 3 or 4 or 5. every process has to have a base address stored somewhere. So you can imagine there's an extra register in the CPU that holds that value. So we've got process 1 sitting here. And remember, each time I say process 1 memory, that's what I'm talking about. The entire memory as far as process 1 is concerned, including its code, its data, its heap, and its stack. There, you just start the stack at the top of the process memory for that one. So process 1's memory, the stack for process 1 would start there. So the code would be there, then the data, then the heap, and the stack would be up here. Okay. All right. So obviously we need to remember a base address for each process. When the process starts, obviously we've got to set up that base address. If we've got to the point now, I mean, we're still not to the point of multi-user machines. Have you got your hand up for some reason, or you're just stretching? Stretching, that's okay. So if we got to the point of processes being swapped out or being suspended and coming back, maybe they come back at a different location. So under this scheme, that's not too difficult to handle. In fact, we just have to load the appropriate base address each time the process starts. And of course, every time you make a reference to any address, you have to interpret it relative to the base. So each process just sees its standard address space, it sees it using these addresses, so we don't have to modify the program each time we load it, and the program is going to just be stuck anywhere. Alright, now you may have seen, I'm sure you noticed, there were some gaps here. Maybe there was a process running here, but that process is finished, so it's not using its memory anymore. Similarly, that. Alright, if some other process comes along that can't fit in any of these unused parts of memory, even though the total size of all those unused parts is big enough to hold, then we'd have to do some rearrangement. So in theory, we could take process 4, stick it down in there because it fits in that slot. Then we would have freed up that amount of space, and we could take process 7 and drop it in there. If we're going to do things like that, every time a process moves, we're going to have to, it's relatively simple, we just have to reset its base address register. So when we compute addresses for that process, they're starting from a different base. So that's okay, and now we're starting to see things like multiple processes sitting in memory at the same time. That's a good start. Here's something else we could do. So far I've been assuming that every process has a continuous chunk of memory that represents code, data, heap, and stack. Does it have to be like that? Maybe it doesn't. Maybe we can do something like this. So if process 7 comes along and it doesn't fit in either of these, well, we could put part of process 7 in here, and we could put the rest of process 7 up here. They're meant to be aligned, they don't quite seem to be aligned. But anyway, that's the idea. So the first part of process 7 goes in there, the rest of process 7 goes up here. That's slightly annoying because we've got the process's address space split over multiple physical locations. Once again, it's relatively easy to handle as long as we have one base address register for each of those segments of the process. So we know that this part of the memory from 0 to A-1, let's say that it actually starts at 1,000. So it's 1,000 starting at address, base address 1,000 up to address 1,000 plus A-1, let's say. That happens to be another 1,000. So up to address 1,999. The rest of process 7's memory lives up here. So every time we see an address that's in between A and the total size of P7, the size of P7, then we have to use a base address starting at here. So let's say that's 5,000. Okay. So when process 7 makes a memory reference, if it's an address in this range, it computes it relative to this location. If it's an address in this range, it computes it relative to that location. Okay. So that way we have the possibility of splitting the physical memory for a process across multiple chunks of the physical memory. So the process memory, which always looks like code, stack, heap, code, data, heap, stack. It always looks like that contiguous chunk of memory, but physically it's actually split across the physical memory. Alright, so obviously I already said this, that every chunk of the process has its own base address. Every chunk of the process has to know how big it is, because we have to know that if I've got an address in this range, then it's relative to a particular base. If I've got an address in this range, it's relative to some other base in the memory. And so each chunk of the process address space lives somewhere in memory. That's basically what I'm saying. So we need a table that gives us information about all of the different chunks that comprise the address space of each process. So process 1 has a total size, and it just happens to be that that's all in a single chunk. Same with P4. Process 7 happens to have two chunks, the first of which is located starting at a base of 0 and has a length of 5,000. So when I say base here, what I'm talking about is a base within the process address space, not necessarily the offset within the physical memory where this chunk actually starts. So once we get to this stage, then it starts to become slightly tricky to, here's an address, where do I actually go in memory to access that address? And I should say, here's an address in the process address space, where do I go in the physical memory address space to access the corresponding piece of data? So I start with the process ID, and I start with a particular address, and I want to know where in the physical memory does that address live. So that's the result of this process to physical mapping. Alright, so first thing we need to do, we need, for the particular process, let's say P7, we need to get this list of chunks. So chunks of process 7's address space. And what we need to work out which of those chunks does this address live in. So the only way we can do that really is to scan along that array and take a look. So let's say we ask for address 10,000. So we go in address P7. So P7 address 1,000. So we get this list or this array, and we look at the first element of the array, and we'd see that it handles addresses 0 to 5,000. Well, 10,000 doesn't fit in that range, so we need to look at another chunk. So we look at this chunk up here, and that the base there is actually 5,000 would be, and the total size is 25,000, so 10,000 fits in this range here. So we know that the address 10,000 is in the second chunk. We know where that chunk starts. This would also, Alright, these are the sizes, and these are the actual physical addresses, okay? So 10,000 didn't fit in that chunk, but it does fit in this chunk here. So we know that it's in the physical memory. Starting at address 25,000, we actually ask for 10,000, so we take 25,000, add 10,000 onto it. That would give 35,000, and that's the physical address location of the object, which is at virtual address 10,000, or process address, if you want to call it that. So this is essentially what all of this stuff's doing. Now, you're not going to do it with a C program, because if every time you referenced a memory address you had to run a little function like this, that would be ridiculously slow. So it has to be done in hardware. So there's going to be some hardware that implements that mapping. Here's another neat trick. So before I said that the chunks of process address space can be arbitrary sizes. What if we make them all the same size? So we're going to divide the address space into 4K chunks, for example, or size P byte chunks. All right, so the process memory has the first 4K, the second 4K, the third 4K, and the final 4K. Now, of course, the process address space might not actually be a multiple of 4K, so you may have the last page with a little bit of wasted space on it. That's fine. Now, these processes can be loaded, these pages can be loaded anywhere in memory. So, in the physical memory, we might have the pages loaded up like this. So page 0 from the process happens to live in the 4th page in physical memory. Second page of the process happens to live in the 2nd page of physical memory, and so on. So for a given process, or for a process of given size, proc size, we know there are going to be proc size over P, we take the ceiling of that, that will be the total number of pages. The other thing that we know is that a given page I always has addresses in this range here. And so it becomes potentially a little bit easier to compute whereabouts in memory a given address is located. So address mapping also becomes a little bit simpler. All we need, because we know all the pages, all the chunks are the same size, we don't need to store that information anymore. All we need to know is where is the starting address in physical memory of each of the pages. So, for example, here we see that page 0 happens to be at this address in physical memory. Page 1 happens to be at this address in physical memory. Page 2 happens to be right at the start of physical memory. Okay? So the page table that the process requires is a lot smaller than it's 1/3 the size of what we had back here. And the address calculation also becomes a little bit simpler. So here's once again the page tables for each of the processes. So process 7 has its first page located at address 5000. It has its second page located at address 3000, and it has its third page located at address 1000. That's just how they happen to end up in memory somehow. Similarly, P4 has 2 chunks that happen to be located there. So you can see that all we're storing here is for each page of the process, we're just storing the base address of that page in physical memory. So if I wanted, so let's say for the sake of argument that these pages are 1000 bytes. If I wanted to access address 1500, I know that it doesn't live in here because this only deals with addresses 0 to 1000. This page here deals with addresses 0 to 999. This page here deals with address 1000 to 1999, and I know that address 1500 must be in that page. So I know where to go and look. I go to page at memory address 3000. Whereabouts in that page is address 1500? Well, clearly it's 500 bytes beyond the start of the page. So I go to address 3000, I add 500, and that gives me the physical address of whatever chunk, whatever piece of data I was looking for. Let's see. All right. I will continue this discussion next time. So just think about that. So we've got to the point, process address space is divided into fixed size chunks. Each process has a table that tells where each of those chunks is located in memory. Okay.